From the Spec Network, this is Fragmented, an Android developer podcast where we talk about building good software and becoming better Android developers. I'm DonnFelker.
And I'm Kaushik Gopal.
Welcome to the show.
Welcome to another Fragment. A friend of mine asked me the other day, "Hey Kaushik, what's the deal with money in programming? I hear you're never supposed to store it as a float, but obviously you want to deal with lower denominations. How does all that work?" Well, 10 minutes after I gave them my explanation, I realized, maybe some of our listeners would be curious to hear my answer too and may have thoughts or, even better suggestions. So in this episode, I want to first dive into the fundamentals of how we think of numbers in programming and then answer the question, what's the best way to just deal with money in programming?
This episode of Fragmented is brought to you by Bitrise.io. Bitrise is a mobile continuous integration and delivery platform for your whole team with dozens of integration with your favorite services. They've got automatic platform and configuration detection, and you can build, test, and deploy in minutes. They also have an open source library of 170 plus integrations that requires absolutely no scripting. You can run the same exact configuration actually locally with the open source command line interface by downloading the bitrise.yml file as well. Furthermore, they have virtual device testing for Android folks. So they have full integration testing with Firebase Test Lab. You can run your emulators quickly and reliably. And you can check that out at the Bitrise blog. Lastly, but certainly not least, is they are hiring tooling and DevOps engineers on site in Budapest, Hungary. So if you're interested, also check out bitrise.io/careers. So again, if you're looking for a continuous integration platform, be sure to check out bitrise.io.
All right. Let's get into some of the fundamentals of numeric data types. Some of you may already know this, so if this starts to sound obvious, we have chapter markers, hit skip, and proceed to the next section. To start off though, we need to brush up on the fundamentals so we can understand our use case with money better. With both Kotlin and Java, we have a whole bunch of primitive numeric data types. So these would be byte, short, int, long, float, and double. Let's start with a byte. A byte has a bit width of 8. What does that mean? Well, since we deal with the land of digital, all things are represented binary, right? So 1 and 0. So if I have a bit width of 8, that's basically saying I have 8 positions where I can enter one of the bits. So I can flip these bits in one of these places. So either 0 or 1, 0 or 1, 0 or 1. This means it can hold a maximum of 2 to the power of 8 values. So some basic math there, but that's basically 256 values. So strictly speaking, a byte is supposed to hold 256 integer values. But integers now could be signed or unsigned. So they could be negative and positive or just straight up positive. Now, if it's signed, that means you need negative and positive values. So split 256 by 2, and we have 128. So 128 negative values and 128 positive values. But we also have a 0 in between, so it's not actually going to be 128 values. Like the value at the very right is not going to be 128, but rather 127, because you got to go all the way from minus 128 to 0, include 0, and from 0 all the way to 127. Altogether, it makes 256. This, my friends, is what we call an 8-bit signed 2's complement. There are still companies out there that actually ask these kind of questions for interviews. So if you ever run into one of those, you can keep this little trick in your head to remember that. Next, we have a short. A short has a bit width of 16. I'll let you do the fun math all over again, but basically what you'll amount to seeing is that the 16-bit signed 2's complement here will give you a range of minus 32,768 to 32,767. By the way, the short was actually infamous in the early days of Android development, and I'll post a link to another fragment that I made way long back if you're curious, and that should tell you the answer. I don't want to give it up just that easily. Look at the show notes and it should help answer that. All right, moving on. We now have an int, also called as an integer, and ints typically have a bit width of 32. Then there's what's typically considered the largest data type, which the largest numeric data type holder, which is a long, with a bit width of 64. Okay, so far, so good. Now, we've been talking only about ints and longs so far. So mostly these numeric data types typically hold only integers. The equivalent of int and long in the decimal world is basically float and double. So if int is the smaller integer data type with a bit width of 32, float is actually the equivalent smaller decimal data type holder with a bit width of 32. Similarly, long is the larger integer data type holder with a bit width of 64, and double is the larger decimal data type holder with a bit width of 64. Now that's all fine and dandy, but if you look at how the values in the decimal world are actually stored, it's actually not as simple as the 2's complement that we just discussed. There's in fact a whole standard that everyone in the world of computer programming has agreed to follow, which will help with this. And that's how we store floats. It's an entire standard. It's called the IEEE 754 standard. I'll throw in some links in the show notes that help explain, what the standard is. But this goes into like some really serious theory. I don't want to delve into the details, but the simplest way I can explain it is like this. Decimal data types, so floats and doubles, are how we represent fractions, right? So 1 over 2 or 3 divided by 4 are all fractions, and they're stored in the decimal format, typically in data type holders like floats and doubles. Now, the way decimal types are represented in computer land, as I just mentioned, is actually a combination of a whole value, like an integer, that is actually what they call a mantissa. This is like some math theory. So it's a combination of a mantissa or a whole number and a base 2 representation. A base 2 representation is basically 2 to the power of an exponent. Now again, don't get too worried about the theory, but basically the way they try to do this is like if you have a decimal point of 0.14, say 0.14 is the decimal fraction that you're trying to store. The way the computer deals with this is it tries to see how it could represent the same thing as a whole number into 2 to the power of another number. So basically all your decimal data types and fractions are represented in programming as, one number multiplied by 2 to the power of another number. Keeping that in mind, here's where things get a little tricky with money objects. For money, we typically need multiples between 0 all the way to 1.0. So 0.01, because with most currencies, 100 of the lower denomination makes up the higher denomination. So 100 cents make $1, 100 cents make €1, 100 paise maybe makes 1 rupee. So most currencies operate on a base 10, and you typically need to represent multiples of 0.1 all the way from 0 to 1. So 0.1, 0.2, 0.3, all the way to 0.9 and rounded up to 1.0 for $1. Now, you know how I bored you a little in the first section with all that number representation theory? This is where some of that will become super useful. We said that decimal data type holders, so, floats and doubles, are represented as a number multiplied by 2 to the power of another number. If you sit with a paper and remember what your high school math teacher taught you, the only multiples of 0.01 between 0 and 1 that we actually can represent properly in a base 2 format are 0, 0.25, 0.5, 0.75, and 1. So quarter, half, 3/4, and 1. That's crazy if you think about it. Take, for example, a fraction like 0.42. That doesn't seem like an unreasonable money amount. That's 42 cents. It could be a pretty common money denomination, but you really can't represent it super accurately or properly with this whole IEEE standard. I know that sounds crazy, but let me throw a direct code snippet for you in Kotlin. So you'll find that in the show notes. If you print 1.03, so, what we would think of as $1.03, minus 0.42 or 42 cents, A normal human being would expect that answer to be pretty simple, right? 0.61, 61 cents. But if you run that snippet, what you'll actually really get is 0.61, 0.00000000, all the way to a couple of few digits, 1. Why does this happen? Well, because of all the theory that we just talked about. This base 2 binary system can only represent those numbers as a finite fraction where the denominator is a power of 2. I'll drop a link that actually explains it better if this still isn't making sense. But basically, in the end, we want the denominator to be a power of 2. And that's why we could do 0.25, 0.5, 0.75, because if you think about it, their denominator, they have a 5 in the numerator, there's a 5 in the denominator, they cancel off, so it remains to have a power of 2 in the denominator. Again, I'll post a link here, you don't get too bogged down with the details. But the thing to remember is this basically does not include most of the numbers that can be represented as a finite fraction in base 10, like 0.1, which is really what the whole money system is based on. That's one class of problems. You can even run into rounding trouble when constantly adding up float values. This is like a whole different problem. This happens again for similar reasons, but it's because certain intermediate values cannot be represented accurately, as we talked about before, so they get kind of rounded off. But that kind of affects the total sum as you keep adding more values in. And so eventually what you'll land up with is a slightly inaccurate value. So let's take an example. Take a float variable, x. Keep adding 0.01 to that float variable. Do this 100 times. The analogy with money is basically taking 100 cents and joining them up, right? What would you expect? 1 or $1, right? Instead, if you write a program where you used a float, what you really get is not 1.0, but 0.99999999934, a rounded incorrect value. This is a common issue with float called a rounding error. This happens because as you keep incrementing 0.1, those intermediate values, like I said, can't be represented. And so eventually what happens is these values are sort of like rounded off up and down, and you get an inaccurate value in the end. So again, look at the code snippet that I drop in the show notes, and you can see for yourself how this actually lands up being a problem, even though you would think it's a very simple. Okay, so we know the problem now, but many computer programmers have built accounting and finance software for a long time. They clearly managed to do it somehow. The obvious question now is, how do they store money in their programs? How can I get 1.03 minus 0.42 to show up as 0.61, like a sane human would expect? Here's the age-old advice. Never use float or double to represent money. I know we talked about like a lot of the theory behind float or double, but that was so we could understand that is not an option. Nope, not a good idea. And the last 15 minutes of the talking that I did should have convinced you of that. If you still have doubt, all you have to do is just look at the show notes, run those 2 code snippets, and remind yourself. So what is the recommendation? The recommendation is actually pretty simple. Use an integer value. Just use an integer value. But store just the lower denomination. So what does that mean? That basically means if I have 1.03, which is $1.03, store the entire thing in the lower denomination, so all in cents. So that would be, that way $1.03 is really just 103 cents. So store 103 in your money object. $0.42 is just 42 cents. So just store 42. When you do the math, you can conveniently just do the arithmetic with the cents denomination. So if you look at the posed question, 1.03 minus 0.42 can just be seen as 103 minus 42, which is, drumroll, 61, because we can do that very easily in integer land. Now, after you've done the money arithmetic, you just convert the cents back to a dollar amount and, you're good to go. So that way there isn't like that rounding sort of intermediate error. It's almost backwards in a way, but it works like a charm. If you check some of the common libraries or API examples, like I think even Stripe does it this way, you'll notice that their money object has a single value and it's typically like an integer value. But while we are at it, I also want to bring up two other important aspects about just dealing with money and the way, you store the objects. If I take my money object, I have that single, int or whatever the integer like data type is that you store the lower denomination in. But as part of the money object, you obviously want to know what the currency is. So, not everyone deals with US dollars or cents. So you want to store the currency type in your money object as well. Finally, and this is so important, I can't stress this more, you absolutely almost always want your money object to be final and immutable. Immutability is the key here. Allowing, the program to meddle or even mutate a money object will just wreak havoc in your system. If you want to do a money arithmetic at any point of time, just calculate it based on those int values that you have from the two, money objects that you're trying to perform your arithmetic on, but then create a new copy and send it down as a result. Don't try to change one of the existing objects and send it back. Don't try to send a money total object that you mutate. Mutation with money is pretty serious. Future you will definitely thank you for this, and past me is giving you this life lesson. Just trust me, you want to always be dealing with immutable objects when it comes to money. Okay, folks, to sum it up, use a single value, integer-like value. Never ever use float or double. When you use that single value, obviously store it all in the lower denomination. Store your currency code with your money object. And most importantly, finally, make sure all your money objects are immutable. Immutability is the key in the game of money. Hope you enjoyed this fragment, and I will catch you in the next episode.
Once again, we'd like to thank our sponsor for today's episode. That's Bitrise.io. If you're looking for a continuous integration and delivery platform, look no further than Bitrise.io. With built-in configuration detection, build, test, and deploy in minutes, tons of different integrations, great CLI tools, and much more. Check it out at Bitrise.io.
That's it for the show, folks. Fragmented is hosted by DonnFelker and me, Kaushik Gopal. We edit and produce all the episodes here on Fragmented. Sarah the Amazing Jackson from the Spec Network helps with production assistance and wraps our final mix. Our theme and ad music is by the national recording artist Blueprint from Weightless Recordings. You can find more Fragmented episodes at fragmentedpodcast.com. Thanks for listening, and we will catch you in the next episode.